Today, I'd like to talk about AI-assisted code generation for HPC. So my background is that HPC guy. So actually, I'm doing some optimization of HPC code, like MPI and so compiler optimize. What to say is that kind of unrolling. I like unrolling things and anything. So, but so actually, I'm not so specialist for the AI agent things, but currently, so you know the increment of the ability of the AI is enormous. So we check the current system like a cloud code. So conclusion, so it is very available and remarkable things to do the performance tuning. So today's topic is very focused on this. Okay, so before starting, I'd like to talk about our project. So in Nagoya University, so we are doing a HPC-GENIE project, so the abbreviation here. So this is a project for the automatic generate of the HPC program using the code generation AI. And aim is kind of obvious, dynamically enhance the productivity of HPC software and automating the whole process for tuning by using the LLM. So this area, you know, currently the prompt engineering, but currently switch to the context engineering. So that's a very important thing. And so my background is software auto-tuning, that's the parameter tuning of the software, also a very important thing. So I'd like to integrate these two different concepts for LLM code generation and auto-tuning in this project. So here is a kind of a member. Let's skip this one. So first of all, I'd like to mention the differences, the computational LLM and our target, but kind of the same thing. So we're using the LLM. But the difference is that I mentioned that I'd like to integrate the auto-tuning technology, the LLM generating system. So the generated code include the auto-tuning functions. So that's kind of a final goal. And next one is that so in the numerical computation field, so accuracy assurance have been studied very long time. So we know the actual error. So with respect to the kind of numerical analysis, so very needed to do the verification of the HPC software. So I'd like to integrate this technology. And so mixed precision is also very crucial things to use the GPU computational unit. So also we'd like to think about this new implementation for LLM code generation. And finally, so we are very focused on the local LLM. So you know the global LLM, like a cloud code, has some problems, you know. So I'll talk to you later. So I think that so local LLM technology will be very effective and crucial in future, I think. So here is the current status and current trend of the quality between the commercial LLM and local LLM. So this line shows the commercial LLM performance. So you see only 7 months gap in there. So that means that we wait for 7 months, so we can able to use a very high quality local LLM compared to the commercial LLM. That means that we wait for their release only 7 months. So very awesome increasement. So that's why we are focused on LLM technology. And another thing that we are focused on the iterative prompting and also AI agents. So to do the optimization, we have many phases like this way. So the first phase is the candidate generation phase, and the second is the selection phase, and the third is the experimental planning phase. And so most of them is most people is targeting the code generation phase in there. So LLM generates the target code, and of course we verification the generated code. So that includes the compilation check, execution test, and also benchmarking inside, and some loop in here. After we get the best candidate, so we back to the first phase. So this is a kind of a loop to do improve the performance for the target code. And so pointing here is that we can also put LLM each phases. So very what to say the enormous things. So maybe you are thinking about this phase only LLM, not so limited. So all phase we can use the LLM. And in pointing here, next point in here is that we can also use a different LLM each part. So if we use some small LLM to generating code, it's okay. And the different commercial LLM is okay, but maybe illegal. But anyway, so we can do that, something like, so very flexibility and very constable loop in here. So, and we are very thinking about a kind of this system. So we are focused on a local LLM system and collaborate with some local LLM. So especially in the Japanese side, we are focused on the Swallow LLM for Japanese university. And it's okay to use the local LLM like ORAMA, it's okay, something. And the target process is code generation, code verification, and performance evaluation, and prompt refinement loop in here. So it should be automated automation. And also we use the lag, and also we use global LLM if you like. So in this circle, if the users want to. And also we need refinement of the target code in our system. And we use a multi-AI agent to inference, so to get a high quality code. So that's all. And there is some many problems there. One thing is that so the refinement is very heavy. So what should we do? So we think about to use the Japanese supercomputer. So that's providing the very large GPU and very cheap ratio. That's only electric charge ratio so providing, and so that's one phase. Also, we can use the refinement thing to use the Japanese supercomputer for providing service. So anyway, so kind of very technical things should be taken into account. So we are thinking about. So I'd like to mention two issues. So one issue is that so the very high charge ratio of the LLM. You see, so if you use the cloud code, so the monthly charge is very huge. So it goes very huge ratio. So the fee of the research grant is reduced. So that's a problem. But by using the LLM, it's charged basically free. So it's very attractive way. Of course, we have a quality program, so we need some refinement technologies. But so the one thing is a very important, what is the attractive thing to use the local LLM. Another thing is the security. So if you are very careful treatment code, so you cannot use the cloud code, of course. So that is not profited for the instance. So in that case, so only choice is using the LLM. That's why it's a very crucial things to do with respect to do that. Okay, so I'd like to explain our experimental prototyping of this system, so by called HPC. So actually, this system is developed by our graduate student, Shinichiro Hayashi. So Hayashi-kun, is there here? No? Okay. And he do that. So he's a very good guy to do that. Actually, so young generation have such a technology. So we'd like to follow him. But anyway, so by using the current AI gen technology, so the prototyping is established, almost established for our pilot system. So before the starting, so I'd like to mention the vibe coding, but maybe you are very familiar. So the vibe coding is proposed by the Direct Kasparty, so very last year. And so the vibe coding minimizes direct writing and user to prioritize instead expression expression intent. So user can observe something, say something, and execute something. So this enables us to rapid prototyping. So this is a very newly concept for the software engineer, I think. And so actually, I don't know the definition of the vibe coding, but this paper defined the 5 kind of categories of the vibe coding. So, and we are very focused on the second definition, so the repeated interactive interaction. So that is kind of a traditional write compile test loop is automated. So that same concept of auto-tuning community, so that we are very focused on this topic anyway. So here is a kind of a dialogue with AI in numerical computing. So actually, this is established now. So this is not so scientific option things. So this is the real things. So if we develop that, I'd like to speed up this matrix mathematical code. Any suggestions? So AI answers. So performance improvement, we can try the following these 3 options. So developer says, I'm not sure what are the best try 1 and 2 first. So AI understands and automated code generation test and all of them. And the result is reported. IJK order and performance A-way unrolling is the best. It achieved 20.8 speed up. So nice. So what about if we try the 3? So they also do checking the auto-tuning for the thread number. So answer is also. This is established things. So now, so kind of amazing. And another one is that so we can talk about AI to think about some numerical computation accuracy. So this code only achieved about 3 minute accuracy. Can you find out why? So in this kind of form, the problem is error conditioned. So and double operation has reached its limit. Would you like me to implement the mixed precision arithmetic? So yes, please. So AI do, just including some mixed precision library and check it all. So, but so the execution time is 10,000 slower. So that developer says that won't be the requirement. So kind of vibe coding. So we do some. So I understand. So I switched the mixed double precision and test it all. So that in this case is we got 1 - 5 accuracy and only speed down is 1.5. So that much is requirement. This is also can do. So in this current system. But so this is a very awesome thing. So we refer to the traditional development way anyway. So this is a kind of background. So I'd like to switch the vibe code HPC current system. So vibe code HPC is a multi-agent vibe coding system developed in the first version in the last year we have established. And the point here is that the vibe coding providing the software developer team for agent. So kind of a project manager, system engineer, programmer, and continuous development for each agent. And also automated, that point. And the target is that also we are thinking about the next flow, FugakuNEXT. It contains the GPU. So, and all of Japanese, almost all many crucial simulation written in Fortran in Japan. So the target is the Fortran to automatically translate it to the CUDA is the point. But we can use another thing. Anyway, so this is the first challenge thing. So early prototype development, we think another so many ways, but finally we use using the cloud code choice. But we can free the cloud code. This is the kind of the prototyping and good for the ability for the cloud code. So cloud code installs the PC, and so any SSH login target supercomputer can be available. So automated for all process by using the cloud code, using the SSH connection and the compilation and submit job and verification, all automated. And I skip it this way. So some kind of a system or organization is something like that. The user cannot do anything before the set the prompting. So currently, multi-AI version is implemented. So this is a kind of the special force, kind of, but not so automated. But the commander is human, and so LLM is a kind of a automated robot thing to do that. And the target is we are focused on the kind of a typical what is the benchmark, Himeno benchmark, from the CFD area. So we do this 4 kind of parallelism. This is a video for the real adapting. So each window allow each window show each agent. And the first phase, so the project manager invocated, so the loading the prompt and plan to how to assign the job. This is automated. And then, so program manager planning finished, the programmer will be invoked by the project manager's order. So this is also automated. Planning and allocation and execution is all automated. And sorry for Japanese, this is report. Report making is also automated. So we don't do that. So this is a wait for the system engineer. So it's programmer 1 agent, programmer 2 agent is invoked, and 3, and 4, like this way. And so the job task is also automated to decide the system engineer. So this guy is MPI open, CUDA OpenC, something like that. After that, so they are talking about each other and doing the making code automatically. So I speak. So in this case, so MPI and OpenMP is the first step they found, and this is a preliminary result. So compare the solo agent or multi-agent with the same execution time. So you see the performance is better compared to multi-agent performance is better compared to the solo agent. So that's why the one thing we should use is that multi-agent is that we get a more nice code with the same time. So that's a kind of a power of the multi-agent. And we also have another thing. So solo agent, some violates several requirements. This is a very, what to say, the I installed later. So that kind of problem. But the multi-agent can be solved. So this kind of problem. So that's why the multi-agent is good. So one thing is that so in solo agent, they cannot find the violation of the requirement. But by using the multi-agent, some agent found the requirement violation and order the agent to fix it. And this is the log. And this log is in the Japanese. English is okay. So they talk each other the Japanese sentences, because that's an LLM. So kind of scientific fiction things that this is real. So I think I'm very surprised to do that. Anyway, so multi-agents have some very merit to avoid the violation of the requirement. And I mentioned one thing is a very important thing is that context length management. So in now, cloud code is of course. So if we use much context length, so suddenly so down. That in case is the automatic auto compact is done. In that phase, the memory is gone, so that means that the performance will be poor. So to avoid this, so we reload the prompting in the first priority. So to avoid this one, so we are starting the monitoring the context length, and so agent checking this coding the auto compaction, and if so, agent found the auto compaction, the order to that agent to reload the requirement or something. So to avoid this, so we can do the long time learning for the AI agent. This is a very crucial one we can find. So anyway, so I'd like to answer another things, but we have almost time. So we are trying to the real application, real application. So this is the cloud code adaptation for the HPC application. This work is by Professor Tetsuya Hoshino in our center. And so hopefully, so you can hear his presentation tomorrow's 11:84 HPC Asia. So please attend this one. So target is that the kind of a Geohem cube written in the Professor Nakajima at the University of Tokyo, and this is the FMM, and kind of a real application, very close to the real application near application. And the cloud code we're also doing to optimize that cloud code. From the Fortran to GPU CUDA code translation. And it says it's easy solver based. So this is a result. So this is human tuned OpenMP and human tuned OpenCC, and this is AI generated. The point here is that interestingly, so the interaction that like make it even faster is very effective. I mean, why? But so it's by setting this prompt, so AI do that very good code. So of course, generated code is poor to the human optimized code, but so good, kind of very good news anyways. So please attend the LM for HPC-GENIE tomorrow, so if you like. Okay, so very quickly, so I'd like to conclude this talk. So with advantage of code generation AI, the process is automated code tuning using the multi-agent. It has been remarkable, I think. And we have developed a vibe code HPC multi-agent code generation system based on the vibe coding. So so many future works. So I don't not mention them very important things. So one thing is the copyright problem and the safe consideration, not so checked. So many papers mentioned this point. Another thing is the code maintenanceability. This is a very headache problem for the software engineering field, but we also can do that because we can also manage the code maintenanceability prompt. So that's kind of the research topics, but we should take care about this matter. And of course, we are now taking a more complex and a very huge line Fortran code. So that's kind of a real adaptability for the LLM-based code generation. Okay, so thank you very much for your attention.